But it is my pleasure today to introduce Dr. Richard Wahls from NASA. He is, I'm not even really reading off of this, I'm just holding it. He's a sustainable aviation expert at NASA. What is your, actually I can check your official title here. So
long to read.
It is long. You've been with NASA over 30 years.
It's right there.
Oh, it is right there. Okay, so yes. So you can read all the words there. But
across.
sustainable aviation is his expertise. And you're based out of headquarters, although you technically sit in Langley.
It's gotten very confusing these days.
Yeah, it's an adventure. So first of all, second of all, I do want to thank NASA for providing you with the opportunity to be here, because actually NASA pays for the travel. We are not allowed to. So thank you to NASA for your presence. And once I hand this mic off, it will be in the center for questions at the end. All right? I'm just going to hand it over to you.
Okay, great.
All right.
Thanks. So I do have a long title that's Sustainable Flight National Partnership Mission Integration Manager. And what I really do is I'm kind of like the senior advisor to the head of aeronautics around the sustainable aviation work. Focused mainly on kind of the near term, which we'll get into, and advising more on the farther term as well. I do a number of different presentations. I think this one, instead of being more centric on exactly what we're doing, although it includes that, this particular one gives me a little chance to talk about the context and some of the challenges we face, Aviation, and just talk about a few issues, but I will show you what some of the main projects are we're doing here. Now, what I like to do right up front, this video is about 50 seconds, but it's goes by pretty quick, and a lot of what you see in here, I'll say something else about as we go on further. So. Was created when my boss, the head of aeronautics, would go to Congress and talk about what we've been doing, so the real progress, real value kind of thing. And one thing I think you'll see through this presentation and what he talks about is we're doing some demonstrations like we've, in aeronautics, have not seen before since NASA existed. And one demonstration in particular is really not like since Boeing did the Dash 80 back in the 50s that we're working on with Boeing now. So you'll pick up on that. So I'm going to go through some vision, some context first, then some of the options to meet the needs that are out there, or some of the things we're working on. We're not the only ones working on it. It's a worldwide challenge. It always is. It's a competitive landscape. And then some implications at the end. Now, one of the things that I really feel is important to do right off the bat is define what sustainability is. Too often people hear sustainability, they have their own definitions. Many people use it as a synonym for climate or greenhouse. That's part of it, it's not all of it. If you look at the UN definition and the definition that we choose to use, it's like this Venn diagram you see here. It's an intersection of societal needs, environmental needs, and economic needs. And if you forget any one of those, you will not find that green spot in the middle there that's the sustainable solution that's good for those of us today and protects the needs of people in the future. It can't be any one of those. I can tell you people in Congress resonated with this chart. There's actually a Congressional Sustainable Aviation Caucus, and they told me they took this chart and adopted it because it gave that holistic view. All right, so a vision for sustainable aviation. Several bullets here. You see the Venn diagram there, that's part of it. But we want aviation to continue to be broadly recognized for its value to society and as a cornerstone of our quality of life and economic prosperity. I think, to me, that's almost a given. Even if you don't realize aviation is affecting your life daily, it is. Subsonic commercial transports are the 24/7, 365 backbone of domestic and global aviation, international aviation. It's not going away. There's a place for the smaller aircraft, but the transportation system we've established serves a very important purpose, and it's not easy to change it dramatically anytime soon. The growth around the world, more so even in the US, but aviation's growing. There's more and more demand, puts more demand on resources, puts more demand on building aircraft and getting them into service. We've got to figure out how to meet the demand. They've got to meet economic requirements, operational requirements, and environmental requirements. The small aircraft, which I referred to earlier, they provide growing value, but they have to be fairly compared with other forms of transportation on the ground, on the water, on the roads, on rail, whatever it is. Gravity's hard to beat. There's a penalty for trying to overcome gravity and fly. It can be done. There's places where you need accessibility, and an airplane's the only way to get in there. We can also use small aircraft to incubate technologies and learn. But in the end, you're looking for safe, clean, quiet, efficient, economical, operable, marketable, aviation. If we dive a little bit further into that, these, for many people, they're no-brainers, but I always think they bear repeating. There's no compromise to safety, ever. The economics have to be favorable to everyone. We want the U.S. to be competitive, but it has to be the whole value chain. You can't have one, entity, the airline making money, or the OEM, or one group making money. The whole chain has to be economically viable, or it's not. The environmental regulations and requirements, they're not going away. They might change from country to country. They might be stronger at one airport than another in some cases, but you're looking for cleaner emissions, quieter, and it's not just the airplanes in operation, but it's the airplanes themselves in the factories, the recyclability of aircraft, the whole value chain. Efficiency in the form of people's time, the energy usage, and the amount of money that's used. Energy, we've been using Jet A for a long time, but you can see that changing with sustainable aviation fuels coming on, and talk about other fuels like hydrogen or natural gas, different types of fuels. We need to be, and we need to look at that like economy-wide, not just in aviation. It's very easy in aviation to go, this is what we're going to do. I know I can get this, but really you can't, because someone else is going to use it before you are. Much easier. So we have to do better at understanding the whole economy-wide perspective. The operability has to be worldwide. The aviation systems can't just work in this country. They need to work everywhere in the world seamlessly. Marketability, I always come back to the value of air transportation. It's the payload range and the speed. There are some things that fly faster, or some things that can carry more payload, but this combination that airplanes have is what brings the value. And we can't forget about that. If you start, cutting ranges in half to get some benefit, then you may not be as marketable as you think, that kind of thing. And timeliness, there's competition going on all the time, and we need to be able to do these changes as fast as we can. All right, some economic stats that I won't read them all, but you get the idea here that it's important to our economy. You see numbers like economic impact in the trillions. It's one of the largest positive balance of trades we have in the country. Millions of flights, millions of passengers, millions of tons of high-value cargo, and millions upon millions of jobs. So aviation is extremely important to our economy as a nation, and to the quality of life as us as individuals. Now, if we look at the global competition and look at U.S. leadership, this is kind of a stark picture of the current state. What I've shown here goes back to 1990, and it's airplane. It says net orders on the side, but since this is all looking in the past, this is actual deliveries. It comes out of the Aviation Week database. There are, I think, I list six companies here. If you look in the database at all the jet airliners that have been delivered since 1990, there's 26 or 27 companies in the world that have delivered jet airliners. There are 5 that have delivered more than 100 in a year. Comac is listed on here, not because they've done that, but because their order book has that coming up in the next 5 or 6 years. Comac from China. One of those 5 was McDonnell Douglas, who's now part of Boeing. So it's a very hard business to get into. It's a very hard business to deliver a lot of airplanes. The competition is fierce, and you see Boeing and Airbus kind of going back and forth, and you see the current state, which I'm sure will change again as we move into the future. The size of the fleet is in the neighborhood of 26,000 aircraft right now, and it's growing. The projection is that we'll need 40,000 new commercial airliners over the next 20 years. That'll be in growth and replacement. If you looked closer at these numbers and you did a little math, 40,000 airplanes is 2,000 a year. And if you look at the peak year in 2018 and you add them up, it's like 1,750. So never before in commercial jetliner history have we delivered 2,000 in a year. Does that mean the 2 incumbents need to produce more, or does it mean there's a third one like coming from China or somewhere else coming up? It's hard to tell, but the projections will need a lot more airplanes. The value of these airplanes, just in selling the airplanes, is in the trillions, $7 or $8 trillion kind of range. So a lot of challenges here. Let's see. Okay, fuel burn. So this is looking at 2018 data. This particular pie chart is global aviation. It breaks it up by seat class for the most part, and that big green wedge there is the single aisles from 126 to 210 passengers. You can cut it different ways. If you look at the narrow bodies and the twin aisles, you end up with about the same. If you add the very large and the small twins together. But that green wedge is, number one, it's where 75% of those 40,000 aircraft are projected to be needed, so high volume. It's a large part of the fuel burn, so the expense and emissions that we use. And the incumbent designs are the oldest ones. We have derivatives that have come into play, but there hasn't been the true clean sheet, unless you count like the A220 from Bombardier, that's on the small end of that, in a long time. And most of the world is looking towards clean sheet single aisles in the 30s. So that's where our focus is looking at technologies that can play into that. And we talk about accelerating change. A normal change would be like maybe a 15% improvement in fuel burn per generation, maybe 20. And we're trying to bring some extra technology forward in time to make that 30% possible. So we'll see. All right, so the other thing about fuel cost is how it contributes to operational expenses to airlines. These data show on the left and in the orange, the ratio of the fuel cost to the operating cost for the airlines. And in the blue on the right, it's the fuel cost per gallon in then-year numbers. You see a strong correlation here. Fuel prices are pretty volatile compared to other parts of the cost. And you see it go up and down, but for the most part, it lives in that 20 to 30% of the 35% box. So a large percentage of the cost is fuel cost, and it's hard to predict because the fuel cost is variable. And to put a number on it, in the U.S. airlines in 2023 spent $57 billion on fuel. I think in 2024, the price per gallon was down a little bit, and it was $50 billion. It's a lot of money, either way, any way you look at it. And any way you look at it, increased energy efficiency is always good. Environmentally, I tried to put together, this was from a few years ago, but just to look at the environmental landscape. There's regulations that are at the fleet level, looking at airplanes, energy, they're operations dependent. There's CORSIA is the market-based measure, looking at the life cycle of fuels. Population, or noise. FAA looks at how many people are affected by noise around the airports. So that kind of level. The International Industrial Group, ATAG, established a net zero carbon goal for 2050. So that's an international industry one, that's not a government one. And if you look down at all the reds and blues here, the blues are kind of airplane level regulations. The reds are more engine specific, where you see like particulate emissions and NOx emissions that affect the health of people. The blues are at the airplane level, so the noise from an airplane, and whether you call it a CO2 metric like ICAO does, the International Civil Aviation Organization, or a fuel efficiency standard, as in the FAA Part 38, it's a fuel efficiency standard. How much fuel are you using? So there's a lot of pressures that somebody who's trying to sell airplanes around the world has to meet from an environmental standpoint, in addition to being economical and keeping the payload range speed that we talk about. All right, we can jump into NASA for a minute, and I have one chart here that kind of, if I look at NASA aeronautics broadly, we do more than sustainable aviation, more than the transport airliners. We talk in terms of transformations, is the term that my boss uses. And if you look at the top, you see ultra-efficient airliners, so think traditional commercial airliners. In the top right, future airspace and safety. And so that's the airspace they fly in, the air traffic management. We do a lot of research in that area with the FAA. But that's also where you get into eVTOLs and introducing supersonic vehicles and how they impact the airspace. So that top right quadrant has a lot of stuff going on in it. The bottom two, I would call them emerging or re-emerging markets. High speed includes both supersonic and potential hypersonic. There's concepts out there for that. And the advanced air mobility, or the kind of the eVTOLs, the UAS, that sort of thing. So you have three that are kind of market centric vehicle sectors, and then an airspace that has to capture them all. When we look at sustainable aviation, it's those airliners, because the vast majority of the emissions and the cost comes from the airliners and the airspace they travel in. And then those emerging markets that I talked about, they really have to be sustainable from the beginning. Otherwise, they're not going to take off, so to speak. So that's how we look at it. If you look at a NASA Sustainable Aviation Strategy, you can go back 15 years or so, and really even further. And we did some exploratory studies. There were a number of companies and universities that were involved in those. And they were called the M+3 studies. And at the time, it was put yourself out in the 2030s, which was way out there in the future. Tell me what we're going to need. Tell me what the world's going to be like. Tell me what technologies we're going to need and how we're going to get there. And we had these studies. We got a list of technologies, a list of concepts, and then over the course of the decade of the teens, we developed some, down-selected some. We worked with their industrial partners to find which ones were kind of both just beyond the drawing board for the next generation, but close enough in that with some government push, we could accelerate them in and make them possible in the time frame of this 2030s next generation airliner. And as a sign, which ones are you willing to cost share on? So we're not just sending out money, we're working with you to accelerate these things. That's how we got to what I'll show you as the Sustainable Flight National Partnership. At the same time, we're not forgetting about the exploratory further out stuff that might enter into service closer to 2050. And so there's a series of studies that are ongoing, but there's some key ones going on right now that are looking with a wider aperture again, things that you have a little more freedom to think about what's possible. Things are more possible in 2050 than they are in 2035, and they're more possible in 2075 than 2050. So that's kind of a strategy that we have. So the Sustainable Flight National Partnership. And I should say that the way we manage this, it's a portfolio of demonstration projects. And although I'm called the Mission Integration Manager, I don't control one dime of the budget for it. I'm more like the advisor influencer guy that tries to integrate them. But programmatic authority still goes through our program directors, and there's multiple program directors going to multiple projects. And I try to keep them all together and try to tell a consistent story about how they go together. So on a chart, this partnership is about accelerating towards revolutionary efficiency and economic impact in the 2030s. If you walk kind of around this airplane, you see engine efficiency and emission reduction, you see airframe efficiency and manufacturing rate. To speak to that, how can we build airplanes faster? You see integrated trajectory management, so that's how do I move the airplanes quicker through the airspace, and then expanded fuel options. And in the case of the SFNP, that really means being able to do different SAFs up to 100% SAF, because in the 2030s, that's what we're gonna have, and anything further out, like cryogenics or all electric kind of stuff, it's further out, so it's not in the scope of the SFNP, it's in that further out kind of work. So we're looking to have globally competitive next generation plus vehicles that can enable up to 30% less fuel and fly the current and the future fleets in a more optimum manner and have more reliable, affordable fuel options. All right, so if we dive into the ultra-efficient airliners, which is where the bulk of the work is right now, we're trying to, again, ensure U.S. industry is the first to establish these new S-curves. So if you think about current systems we have and the evolution of them, having a slightly better, important improvements, but an evolutionary improvement in wings or the weight of an aircraft, that kind of thing, higher temperature material in an engine, those things still need to happen. They still need to happen. What we're trying to do is get on a new S-curve where you change the architecture to a composite single aisle wing instead of a metal single aisle wing, a 50 OPR pressure ratio on an engine that has 3 pounds of mass flow through the core, for example. A truss brace wing or a blended wing, something different that brings value, not just doing it because you want to do it, but something that brings value. So as you walk around this chart, you see electrified aircraft propulsion, and so we're working with 2 contracts there that one of them is focused on turboprops, one of them is doing a turboprop demo, but it's focused on how do you bring electrification into a gas turbine for an airliner. We think, it says about 5%, I think it's probably 3% maybe. That would feed to what you see on the bottom right, the efficient small core gas turbine, where we think you can get up to 10%, and maybe 3% of that's coming from electrification on the core. That doesn't include what would happen with the propulsor part of the engine. As you move up, we're trying to increase the manufacturing rate of composite single aisle airliners by 4 to 6%, or 4 to 6 times, not percent, 4 to 6x. And we think that the number there is 5 to 8% fuel burn if you can do that on fuselages and wings on the single aisle compared to the metal alternative. And then aerodynamic efficiency, we had a competition and we settled on the truss brace wing. The DoD is working with a company called Jet Zero doing a blended wing demo that builds on 30 years of NASA research with Boeing and others. But the truss is what we went with here, and depending on the trades, we see 5 to 10% coming from the truss on top of everything else. And it's got a high wing, which means it's got more room potentially for a larger, more efficient propulsion system. So there's synergies there. At a high level then, when we set out this plan in 2021, we looked out and said we need to do these demos somewhere in the 25 to 28 timeframe so that industry leaders would have the information in hand to make well-informed decisions by the end of the decade for products that could enter in the 30s. The amazing thing to me is that all those first flights or first tests, although they've drifted to the right with budget and time and challenges, they're all still in the box, at least when they start. And so they're still highly relevant. This is at the core of me saying, keep the foot on the accelerator. We can't slow down, but they're still happening. We've made progress, so some of them have selected the partners, we're making progress. We're getting through the reviews. And I wanted to mention the top row here, the model-based systems analysis and engineering line, is I often get asked, is that truss brace wing vehicle going to have all these technologies on it? And the answer is no, it's not, because if I had to wait for the engine technologies and the composites to be ready, then that demonstrator would be in the 30s. It wouldn't be in this decade. So what we're going to do is, with model-based systems analysis and engineering, is integrate the benefits of these separate swim lanes into what we think is possible. And of course, what really matters is what industry thinks, not what NASA thinks, but it's what we can show we think is what might be possible. So if we walk through these a little bit, the transonic truss brace wing started back in that 2000. It's an old idea. It's not a new idea, but it had a renewed life with the work with Boeing and NASA in the 2010 range, and we got to where we were doing wind tunnel tests, and this is just some of the wind tunnel tests. The 2013 test was the first flutter model of a truss brace wing. We were really worried about long, thin, flexible wing. Is it going to flutter? Am I going to have to add a lot of weight that kills the benefit and it goes back on the shelf? It didn't do that. It looked pretty good. It didn't look without challenge, but it looked pretty good. We did performance tests, high lift tests, and we're continuing to do tests around icing and looking at noise and high lift system integration, that sort of thing. And if I showed this video that does not have sound, so don't worry about the sound on this one. This shows kind of the level of fidelity of some of the models. This is a low-speed model in the 14x22 tunnel at NASA Langley, and you see NASA and Boeing people working together on it. And this test included ground effects, because we hadn't, it's not like it hadn't been done with a high wing before, but not in a while, and not with a strut like this. So we did select Boeing to do what's now known as the X66 demonstrator, and so what you see here is MD-90 that Boeing bought 3 of them, and one of them is in the process of being modified to include a truss brace wing. So it's not a, so it's a learning vehicle. I'll show you in a minute what actually comes off, but the engine comes off, the wing obviously comes off. There'll be some modification to the fuselage, but it's not going to be like an optimum best fuel burn you can get kind of vehicle, because it's constrained by being a modification to an MD-90. And so what it's designed to do is to be a learning vehicle to teach you how well your tools predict, how the structure acts, how real structure acts, not wind tunnel model structure acts, how the aerodynamics work, how you can pack systems into a very short chord, thin wing. It's going to drive a lot of innovation, whether we end up having a truss brace wing or not, just because of how you package an airplane. So that work's underway. And this picture here, the green are the parts on the MD-90 that are going to go away, and this will give you a sense of scale. You'll see the X66 has a larger span and it's shorter, and it's going to have modern geared turbofan engines instead of the older ones that came with the MD-90. And then when it takes to the air, right now planned for 2028, it'll look like that picture there on the left. So that's pretty exciting. I don't think we haven't done anything like this in many, many, many decades. in the commercial world, for sure. In the composites world, high-rate composites. So we already talked about how many aircraft we need to build. I think there's recognized value of composites over metals. They both have their pros and cons, but there's a desire to get composites into the single-aisle class of vehicles. We all know that the single aisles, before COVID, Boeing and Airbus were getting up into like the neighborhood of 60 a month being delivered and trying to get to 70 or 80, and they're not back there yet. But on carbon airplanes, and there are a couple single aisles. The A220 has a composite wing, and there's a Russian plane that has a wing and composite wing. The 787 does, but they're all built, on the order of 10 a month or less, maybe 15 if you have 2 lines, but nowhere near 60 or 70. And so a key part of this chart is on the left, you see how composites have worked their way into aircraft, and you're trying to get the benefits, the performance benefits and operation of the composites. But there's also another relevant environment when you're doing this kind of technology, and that's the factory floor. And I think it's not that the factory floor was ever ignored, but I think it's been elevated to almost an equal level here of how will a certain technology work in the factory? How fast can you make something? How much will it cost? And keep the benefits. And so we looked for composites beyond what's already being used today into resin infusion and thermoplastics, for example, that has some legacy. And then we're taking a look at the layup, the cure, the assembly, the inspection, the paint, every process with a consortium of about 20 companies and universities in the country, and trying to play these different technologies for both the wing and the fuselage kind of application. And in our phase 1, it started with looking kind of down at the subcomponent level. Can you inspect? What would a component look like? And we're working our way up to where phase 2 proposals are in development right now. And with the current budget, we would have both a wing and a fuselage demo in the 27 to 28, probably starting in 27, and the second one maybe a little bit after that. But it's not going to be like a full single wing, because part of what the team has decided is take the relevant part, the wing box, build it a certain way with the different technologies, and build replicates, because you want to see, can you build the parts repeatably? How do they behave repeatably well? That sort of thing, and how much do they cost, and how much do you learn by doing them? And we intend to do that on wing relevant structure and fuselage relevant structure. If I go to electrification now, and this is a video from that GE made, our partner GE, and so they have a Saab 340 aircraft, and GE's partner is Aurora, a Boeing company, and the airplanes at Aurora, it's going to be modified with these electrified powertrains. They're going to be able to fly it on, with gas like normal. They'll be able to fly in a full electric mode and a hybrid mode, and you're learning about what it takes for a 1 megawatt level powertrain. And in GE's case, they have an eye towards taking this technology and what they're learning and putting it into their RISE core, their concept core for the next generation engine, in a very mild way. You don't have to plug it in, but you use it to kind of make the gas turbine more efficient. The other partner is Magniex, who is just north of here in Everett, and they're squarely focused on a turboprop application, also at the megawatt class level. And they're working to do this research with an aim towards certifying a system that could go on. This is a Dash 7, but other aircraft where they could retrofit turboprops. And we're learning a lot about the certification process and the safety process that isn't exactly like what an airliner would face, but it teaches you something along those lines. So that hybridization will feed into what we call the small core, or the hybrid thermally efficient core. In phase 1, we had Pratt & Whitney and GE were competing. This core engine, and so you could see this picture is shown with a ducted propulsor, but it will, we're working the core, so it could work with an unducted propulsor like CFM is advocating. We're working the core. How do you make that core more efficient without having it grow in size, get more mass flow through there, working the different components, and also enabling like up to 20% power extraction that could be used back in propulsion, or it could be taken to other systems on the airplane. Using different NASA facilities and industry facilities to do this. And so this gives you a stationary walkthrough that shows the power extraction, combustor work. The combustor work is to help ensure you're compatible with sustainable aviation fuels, for example. The turbines and the compressors, and you see advanced materials there. So there's coatings for high temperature. There's aerodynamics using the modern CFD for the blade designs, that kind of thing. And you get tipped turbine blades that are like the size of a dime, incredibly small, high temperature, high pressure type work. All right, airspace. So I mentioned like optimizing trajectories. So in the airspace world, NASA does a lot of research that works with the FAA and the airlines. We have a similar map where we've laid out these SF&P operational demos, the cleverly named 1, 2, 3, and 4. But at the backbone of these, you used to hear about the airspace system being talked about as next gen. This is about infocentric net, having a digital platform where services could be offered to bring more efficiency in. And this first demo that's ongoing right now, it's been ongoing since 2022 in the Dallas-Fort Worth area in the live system, looks at departure, making departure more efficient. And I'm going to show you a video that has sound on it. These other demos will look at other use cases like approach and en-route trajectory and other things like that. So I'm going to go on to this video, and this one will explain better than I can usually about what they're doing here.
NASA's Digital Information Platform is creating a digital information ecosystem to exchange services and provide access to airspace information to enable fuel-efficient operations. This system allows providers to make their services more accessible and consumers to access information and services they need to optimize their operations. In this video, we will focus on the collaborative digital departure rerouting service, which provides airlines with routing options similar to how drivers navigate using cell phone apps. Even though you know how to get home, the traffic conditions on the roads can change which route is the quickest and most efficient. The app will then recommend new routes that are faster and more efficient, even if they are a little longer in distance. In the sky, flight plans filed by flight operators may experience delays due to weather or increased demand for the same route. Alternate routes may exist that could reduce potential delays for a restricted route, even though they too may be a little longer. NASA has developed the Collaborative Digital Departure Rerouting, or CDDR, service to identify these routes and evaluate their predicted departure delay savings for airlines.
So it's a lot like Google Map, but for airplanes, and it's been active in Dallas-Fort Worth with American Airlines and Southwest, I think. There's 3 or 4 airlines, and just recently it's active in the Houston area now, being demonstrated again. It was fascinating to go down and see the place. And American Airlines Dispatch Center, and I asked them, what are they going to do when it goes away? And they said, well, don't take it, we need it. So, well, okay, you got to work with the FAA and the other companies to spread it everywhere. So on a beauty of something like this is it works on today's fleet and tomorrow's fleet. The numbers on an individual flight basis are relatively small compared to the 30, they're really small compared to the 30% when I talk about on a certain vehicle. But when you multiply them by all the airplane operations, the numbers add up. And it can happen now, or as soon as you can deploy it. So it's different from a vehicle design in that regard. We're developing further capability, look at other parts of the flight envelope to deal with that. I wanted to mention contrails. Contrails is something that the science community, in my experience, so there's general agreement that contrails overall provide a net warming impact, but being able to predict that on an individual contrail basis is, some people say we're good at it, some people say we're not. And whether you believe in the warming or not, the Europeans right now in January initiated a monitoring and reporting system on contrails. And that's, you could step ahead a little bit and figure that at some point there's going to be penalties, like there are noise penalties at airports for forming contrails that are believed to be warming. And so it's an economic issue for airlines. That's when they come to us, they want to know, is it real? How well can we predict them? Can I predict them better? And so we're trying, we don't have a lot of budget for this, but we're trying to help advance the science so that we can understand how to make, what the economic implications will be from contrails. And what you see here is, we did a test, this was October 2023, where we flew a DC-8 with lots of instrumentation, and there were international representatives on the plane with their instruments, and we flew behind the MAX with the LEAP engine, which was the leanest burning engine, and flying in and out of the contrails. I got to fly on it. It was really fun. You had to be buckled in when you went through the contrail. But you didn't when you were flying above it, shooting a LiDAR down, taking 3D pictures of the contrail. It was pretty cool. This is a short video that I want to set up real quick. It's on the left, you're going to see data, time-wise data going across. It shows relative humidity, the number of particles, and the CO2. And on the right, you're going to see where this was not the one in Seattle. This was actually in Germany, but it's a really good video. And if I play it, so you can see the contrail, and it exists, and the relative humidity is up above, the ice supersaturation is up above 100%. And then in just a moment, you're going to see that blue line dive, and you're going to be out of ice supersaturation, and that contrail is going to disappear. It's going to go, it still forms up right near the lead aircraft, but it's gone. So what I ask you is, when you look at this, you say, okay, it's daytime. In daytime, the contrails are usually cooling anyway, but I'm doing an experiment. Look at all that cloud cover down there. Does it even matter if you have a contrail, if you have all that ground clutter? The scientists tell me it depends. Depends how high it is, all that. And if you predict it's going to form and then it disappears, should I have avoided it or not? It really needs to persist. It needs to persist at nighttime. Then if it persists at nighttime for hours and spreads, then there's pretty general consensus that it has a warming impact. So my message is that contrails are complicated. There's some things I think we know, but there's a lot of things that I think there's still division in the scientific community about whether it's safe to go and avoid them. And if you avoid them, you're putting more carbon in the atmosphere, and there's trades with that if you believe in climate change. And so it's complex. All right, so early on I mentioned we did the N+3 studies where we were looking forward to the 2030s, and we had other projects that looked into different decades. And we have these studies going on right now that look out to the 2040s, that open the aperture a little bit more. One way to look at this is, and I'm still trying to improve this chart, but if you look at things as like evolutionary, as things, like I said early on, are kind of improving the current system, which are important to do, versus things that are revolutionary, that are like a step function change to some architecture in aviation, to something that I'm calling transformational, that is like the energy infrastructure beyond aviation changing and how that feeds back into aviation. There's different levels of change that are different degrees of possibility and difficulty and benefit or risk, however you want to look at it. And the evolutionary type work is still important. It's cross-cutting. The demonstrations that I showed you, I think, are revolutionary because they do change architectures. Once we jump on that new S-curve, then they become evolutionary. So you make the step change and then you have to evolve from there, because you're not going to have the perfect answer on the first try. And then we're exploring these transformational ideas. And like the N+3 studies that you can look up from 2009, 10 and on, we have something called ACES, that's Advanced Concepts for Environmental Sustainability, and there's 5 teams that have been awarded contracts that are looking out to that 2050s time frame. They're supposed to tell us what the world's going to be like. They're not constrained to the 2030s, where certain things are possible and certain things are not possible, given the time you have between now and then. So the aperture's wider open. You can consider cryogenic fuels and breakthroughs in electricity, electrical storage, that sort of thing. Those are ongoing now, so you want to watch for those. So just to leave you with a couple things, think about the implications for sustainable aviation, and hopefully you've got some of this message kind of throughout, but I think time is critical as demand is growing and global competition isn't waiting. So it's not sufficient to just, we can wait another year, even though that happens. But I try not to let that be acceptable. The energy sector transformation is happening. The grid needs to be green for all sectors, including aviation, because a lot of electricity gets used in aviation, even if it's not to power airplanes today. So keep that broader perspective. Energy efficiency is necessary, absolutely, to keep improving that, but it's not necessarily sufficient to solve all the problems that we have. The fleet, the size of the fleet and the infrastructure, the inertia of the fleet is huge. And it becomes extremely easy for people to go, oh, it'll change, and we can do this, it'll do. Very hard to change. Doesn't mean it won't, and it doesn't mean it won't slowly change over time, but it's try to be realistic in kind of time horizons. And what some of us call the business physics, how the business of aviation works, what the flexibility of an asset, can I cut the range of an airplane in half? And now an airline might have to own 2 airplanes. Is that reasonable to do? That's also slow to change. It changes, it's changed over time, but it's not going to happen overnight. And how these transitions happen, I think, is a pretty big deal and an unanswered question, whether it's the fuel or whatever it is. So my last chart is just to remind you that, commercial air transportation of people and goods is critical to our life, our quality of life. You miss it when it's gone. In COVID, cargo kept going. So, and it's, the airliners they're not going away anytime soon. We may see introduction of supersonics, we may see introduction of EV tolls. They'll add value, but the core isn't going to dramatically change for a long time. It's complex, there's no silver bullet solution. You got to be working all these different types of solutions. They all have to work well together globally, and this isn't a time to sit back and wait and say we have time. But at the same time, if you jump too soon with a solution that's, before these demonstrations, I believe these demonstrations are important and can change the world. So I don't want decisions to be made before we're done with the demonstrations, but we can't slow the demonstrations down. And so I just said the last one. I think what we're doing is important, both for what's coming up in decisions at the end of the decade for the 30s, but also for setting the stage for what comes beyond that. So with that, I will stop and see if you have any questions.
If you have questions, there's a microphone in the middle, and then online, David is tracking.
This guy is someone I learned a lot from early in my career and throughout my career. So,
when I was working HSCT and Sonic Cruiser and some of the N+2, N+3 stuff from the aero side, we got pushback from our structures people on the difficulty of using their preferred manufacturing methods for composites due to local curvature and span-wise curvature.
remember the potato chip?
Yeah, and
NCVers.
BWB, I think, also has some issues with that maybe they'll encounter when it gets along far enough in their demonstrator. But is your high rate manufacturing for composites doing anything to address being able to give more freedom, shape freedom, or is it just focused on a simple box at this point?
So I would say that they're considering these alternative configurations. I don't think there's a specific focus on enabling a potato chip, but people talk about gull wings and other things with a higher curvature, and so that's all part of the mix. But the demonstrations, I think, because of what they're trying to demonstrate, are going to be kind of core boxes and with the spars on the wing, and there isn't going to be anything dramatic, I think, specifically tested there. But I remember some of those designs. The one where we let the numerical optimizer just go and see what it would produce independent of realism for structure. Yeah.
So, thank you. It's actually pretty inspiring.
Good.
One of the things that we're doing is also inspire students. And you had a graph of the sales of airplanes. And there was a huge dip, which I'm pretty sure was the pandemic. But then
Yeah.
Airbus recovered pretty fast, and the US with Boeing didn't. And one of the challenges is, as you were saying, who's going to win this next one, let's say. What's the real collaboration has worked pretty well in many cases. Is this really a competitive stage at this point, or is this a collaborative stage?
Well, there's definite competition is going to stay between the companies and the countries around the world. I think you see collaboration in, like, through ICAO, where like in this current cycle, there's been study to look at, should we change the noise standard and the fuel efficiency standard, that I've been on those ICAO committees, and the industry folks are observers officially on those, but very active, and the industry speaks with one voice when they come to that international realm. And for the environmental standards, I think the same I feel happens in the safety world, because one of my other points was you needed to have, like, global operability, global compatibility in systems. And so there's a lot of areas where there's a lot of collaboration to have everybody be able to work together, but then you get to that competitive part of, how much performance for how much cost, and then it's going to be, hard to really collaborate. there is, you go to conferences and you see, I'm pretty good friends with the executive director of EU's Clean Sky, Clean Aviation program, and we talk a lot, and he comes over to AAA conferences, and they share a lot about what they're doing without sharing the secret sauce, and I would say we do the same thing. And when we work with the Boeings of the world, they know that as representatives of U.S. government, we need to be able to share stuff that everybody can gain from, but I'm not going to share what gives away the secret sauce. And so there might be some things where scales come off, and you see, we kind of learned this, and our codes, can compare to that, but I'm not at liberty to tell you exactly how we did it if there's certain arrangements in place, and that's for U.S. competitiveness. So,
Thank you.
So a little bit of both. How was that?
I have another one.
Okay.
So, again, with the students in mind, the teaching professor is talking, so if research wants to stand up, go for it. Really, sustainability is always like a key word that everyone wants to teach today. But I like to look at it as, should we be changing any teaching fundamentals about what we're teaching students? Is there a new class that really should be taught, not about the concept of sustainability, but about, I'll put it this way, the math behind it? Is there anything in here that we as academics should be teaching students more than concepts, like hardcore something?
Yeah, so it's hard for me to say that there's any of the traditional disciplines that you can skip. So I think all the traditional disciplines, and we've gotten, I think, better at the multidisciplinary merging of the disciplines. And how do I do an aircraft design? What probably doesn't sink in as much is for lack of a better word, and we have a paper on this, that's the ILITs, the affordability, certifiability, manufacturability. And so, we focus a lot on the design of the vehicle, and this is the performance it has. And I hate to sound like an MBA, but some of the business parts of it that factor in, to design decisions. Maybe some of how I know I didn't learn anything in school about routing and how the airplanes are used and how the airlines think. It was more how you design the airplane, and that kind of stuff. As I've gone through my career, I continually learned more about the disciplines, even the one I spent most of my time in, aerodynamics. You can never stop learning that kind of stuff. But as I evolved further, those kind of non-traditional parts and gaining appreciation for those types of trades that we don't normally think about, I probably could have benefited earlier in my career. Of course, if you learn them in a class, you learn them for the class, and if you don't get to exercise them, they don't necessarily stay with you as much. But I think if I'd heard them more, I might have appreciated them a little bit more. I also, it was sort of a joke, but people talk about autonomy, and at one point, my boss was, talking about hiring people to do autonomy, and I'm like, well, that's, a controls guy applying it, a logic guy applying it. And I've never seen a job application for an autonomist yet. So do I train someone in autonomy? I don't know, but you could, it's like, and you could find a merger of all those disciplines and train someone like that if you wanted another specialty. But some of these things are good old-fashioned traditional, basic physics, and then applying them in a new creative way also.
Thanks.
This is a question from one of the observers online. Do you think that industry will adopt the sustainability proposal without regulatory pressure?
So I'm not sure what's exactly meant by the sustainability proposal, but I think that all the technologies I showed you, whether you call them sustainability or not, they're good for business. They drive towards more efficiency, so less cost, less energy, less emissions. And I think that if the demonstrations prove out, I think they have a real chance to be adopted, and then you get into that whole realm of business physics in certain trades that don't have anything to do with whether what I just proved to you is possible. Does it fully buy its way in? But they'll be motivated to, and I think the best sign of that is the amount of cost-sharing money that our industrial partners are putting into these, not out of the goodness of their heart or just because they're curious. It's because they think there's real potential. So I think the answer is yes.
Any other questions?
Is the work toward X66 including work to try to address some of the questions that came up about TTBW certification, like crash worthiness of having the wing on top of the fuselage, bird strike on the struts,
Yeah.
those sorts of things?
So we have, the work on the truss brace wing that started in that 2009 timeframe evolved to the point where the X66 was needed as a spin-off project to do the full-up integration with real structure and all that. The kind of the original home project is still doing cost-sharing, cooperative work with industry. And those topics are still on there, and some of them we're doing cooperatively, some of them we're not yet. But something like icing, I've seen, it's actually fascinating, but the chord of the full scale kind of vision vehicle, I don't know, 6 feet. It's not big. So you could put full scale into the icing tunnel at NASA Glenn in the region where the strut comes up and joins. So we had a section of the wing where the join was, and it's not been published yet, but we've run that in the icing tunnel. And part of it was to see how, so the wing is swept more than the strut, so you have sort of a closer to a 3D and closer to a 2D. And so how was that interaction going to play with icing? And I saw 1 or 2 runs. I get lucky, I get to go in and watch some things like that, but I haven't seen kind of the results, and they haven't published that out yet, and there was going to be a second test. So that's an example. The other ones you mentioned, I think those are not in the current contract, but that doesn't mean they're not being done. There's work looking at an integrated, higher Reynolds number, different high lift system integrations, that kind of thing. We did tests in the 14 by 22, and we're looking at a slightly higher Reynolds number now to look at different high lift system integrations to provide better understanding of the trades there. That was a pretty high priority.
Any other questions? All right, well, thank you. Join me in thanking